Hello everyone, I'm Willis T and I'll be covering my final year project, which is hardware-assisted malware detection for embedded systems. For this project, the following items listed on this slide will be covered. In this project, the goal is to create a lightweight malware detection prototype suitable for resource-constrained embedded systems. A popular hardware-based detection technique, hardware performance counters, HPCs in short, will be used as a metric. The prototype employs a statistical method based on t-tests, which aims to quantify the difference between benign and malicious applications. The prototype utilizes indicator observer tuples to distinguish between benign and malicious application. An indicator is defined as any operating system program the embedded system supports, while an observer is defined as the hardware events the embedded system supports. HPC profiles will be collected for each benign and malware application in the training set. Similarly, HPC profiles will also be collected for applications in the test set and compared to those in the training set. An evaluation for the applications in the test set is performed. Hardware performance counters form the basis of our prototype. Primarily, HPCs count the occurrence of hardware events. In addition, HPCs are non-invasive to running applications and are readily available in modern processors. With the use of Linux Perf, a performance monitoring tool, we can capture HPC values for applications. The goal is to create two general profiles, namely the benign and malware applications. HPC profiles of malicious applications should differ from benign applications, as seen in the figure on the right. The system the prototype is running on is the NVIDIA Jetson Xavier NX Developer Kit with a 6-core ARM v8.2 processor. In addition, the prototype, lightweight analysis of malware for embedded architectures, or LAMBDA in short, is run on the system. In the calibration step, HPC values for applications are collected. Afterwards, the application has split into train and test sets, and the model will be trained and tested accordingly. The prototype is based on a statistical t-test approach, which estimates the difference between two group means. The null hypothesis proposes that there are no difference between certain features of a dataset. To reject the null hypothesis, the HPC profile of the malware applications must differ from that of benign applications. The HPC profile is populated when the indicators are run and the HPC values of the observers are collected. For the benign dataset, the ME-bench embedded benchmark is used as it provides lightweight embedded applications. As for the malware dataset, ARM-compatible Mirai malware variants are taken from VirusShare. An overview of LAMBDA is presented. Firstly, the benign and malware applications are separated into training and testing sets. HPC profiles of the training applications are collected during the one-time characterization using Linux Perf, a performance monitoring tool. A visual representation of the collection process is shown. While the application is running, the indicator programs are also run concurrently, and HPC values of the observers are collected for 20 samples across an observation period. A trained model is generated, and HPC profiles of the testing applications are collected similarly. The model compares the HPC profiles and produces a benign or malware output. An example of the benign and malware output is shown. Do note that there are two evaluations for each application, which will be covered in the next slide. LAMBDA performs two types of evaluation, an offline and online malware detection. The key difference is the origin of the HPC profiles for the test dataset. In the offline malware detection, the HPC profile of the test applications are collected before the model is trained, whereas in the online malware detection, the test applications are run and HPC profiles are collected in real time. The F1 score for the offline and online malware detection are as shown. The F1 score for the online malware detection is lower, and this is attributed to random process spikes during the real-time collection of HPC values, which impacted the accuracy. To conclude, the accuracy of LAMBDA is heavily dependent on the indicator observed tuples and the weights assigned to them. LAMBDA is meant to be a lightweight malware detection tool, which employs statistical method using t-tests to distinguish between benign and malicious application. Although the accuracy may not match up to computationally intensive state-of-the-art tools, LAMBDA is suitable for lightweight security, especially in resource-constrained embedded systems. For future work, more experiments can be conducted for different benchmarks to verify the robustness, and LAMBDA could explore the use of other indicator observer tuples. This is the end of the sharing. Thank you very much.